Hello, those watching the recording. I'm David. I'm coordinator of the Maths Learning Centre at Semester 1, 2024, and this is a revision seminar for data analytics. And that's enough of my face for now. There we go. It's clear enough. Okay, so I've had some lovely friendly people here, and they have asked me to talk about regression, and in particular, the hypothesis testing that goes with that. But I may just talk about some of the other things in there as well. And I've had a good look at what's in the My Uni, and we'll see how we go. Okay. So, regression is a statistical procedure designed to answer a question that goes, how do you predict one thing from another? So you go like, how can I predict y from x is the question that regression is asking, and y could be anything and x could be anything. So how can I predict my sales from the amount I spent on advertising? How can I predict the number of likes on my Instagram post based on what time of day I do it, and whatever. There's anything you can do, but you can try and predict this using this. And what it produces is a formula. And what that formula is called is the regression equation. But the formula will be something like y equals something, and there's an x in the formula there somewhere. But actually, even better, it usually looks like this. It looks like number plus number times x. That's what the formula normally looks like. Does that look familiar? Yeah, cool. All right. And that's the goal. The ultimate goal is to try and figure out a formula that based on whatever x is, you can try and predict what the y should be that goes with it. Cool. But the problem with that is that you know for sure that it's never going to be exactly the same. Like, even if you post at the same time of day, the number of likes will be different, probably because there's other reasons, but there's always some random bit that makes it different. So the idea is that you draw this graph, which is a scatter plot, and you go, based on this x, there might be this y or this y or this y. There'll be all these different y's that go with every x. And it may be that in general, yes, the y is higher as the x gets higher, but it's not like you can predict exactly what the y is for every given x. And so there's this randomness involved. And so when a statistician or econometrician writes down this formula, they say the actual value of y at position I in my list is some number beta naught, which is this number here, plus some number beta 1, which is this number here, times the actual value of x at position I in my list, plus a bit, which could be positive, could be negative. That's the bit that's above or below the line. And so this bit here is the line, and this bit here is the up and down from the line. Okay, and this is a theory saying that this is how the universe chooses its values for y. It does this calculation, and then there's a bit of random extra, possibly up, possibly down. And the big problem with statistics is that you will never, ever know what these numbers really are, because there's so much randomness that there's all these different choices for what it could have been. And you don't know that maybe most of the randomness was positive today and the line should be here. Maybe most of the randomness was negative today and the line should be here. You don't know for sure. And so what you do is you do this calculation that will put the line as close to the middle as possible. And the way it does that is it takes these, a second, there's words for this. This is the intercept. This is, does your lecturer call it the slope or the gradient? And this is usually called the error. which is a technical terminology. It's not like it's wrong. It's just different to what you would have predicted. So it's not an error in terms of a mistake. It's an error from an engineering, some physics point of point of view. It's like, I don't know, it's just come to be called that. That's why it is, yeah, but technically the residual is how far your drawn line of best fit that you drew today is from the real answer, whereas the error is how far the imaginary correct line of best fit that we can never know exactly is from the real answer. It's a hypothetical error. Is saying like, yeah, it's hypothetically what the universe chose for the error, but we'll never know exactly what it is because we can never know exactly what these are either. So that, yeah, but that's the difference. So the residual is trying to be our best possible guess at what the error really is, but we never know for sure. Does that answer that? Yeah. Yeah. And so like we'll never know. For sure, any of these things. We definitely know the Y and the X for sure, because we actually wrote them down from an actual person, or maybe they're not people, maybe Instagram post or whatever they are. We actually wrote these down. We definitely know what these are. And the I is referring to where you are in the list of data. So this is the position in the list of data. That's what the I is referring to. So we'll never know these. We'll never know what this really is, but we can make a really good guess. And the theory of ordinary least squares regression is how to find the best choices for these that we can based on the probability theory and the calculus. So our good friends Fisher and Pearson back in the 1890s figured all this out. It was very clever, but that usually means it's difficult to explain. So yeah. So that's the idea behind it. And then what we're going to do is we're going to get the data and we estimate beta naught, and that gives you a beta naught hat. Or if you like, a little b naught. Your lecturer seems to use both. And we estimate beta 1, and that's beta 1 hat, or if you like, little b1. That, as far as I can tell from reading the MyUni, they're the same thing. Could be wrong, but pretty sure this is the most official version. It may be that this B naught and B1 are just any old choice for what these could have been. But yeah, I'll talk that through in a second. And you also estimate the errors there, and what you get is the residuals. I think it's called UI, but I could be wrong. It might be RI. I just didn't see it there. I'm just going to put the word residual. All right. So that's what we do. We get the data and we calculate all these things, and there's formulas for what these things are, which I will copy onto my page in a second. But that's the idea. And the kind of I have this picture in my head of how this works, and it goes like this. This is our actual data, like that. And what you do is you try all the possible lines that you could draw. So you try yi equals, not yi, just y equals b naught plus b1x. And the reason there's no i's on this one is this is supposed to be a formula that works no matter what, no matter whether there's i's or not. So you try that for all different b naughts and b1s. And I think that these little b's in the notes are not what these are, but they are what they could have been. And so we try all these different ones, all these different possible lines in all different places, and we try and find which one is the closest to our data. And it turns out that if you figure out, okay, so that's try different lines, and that means trying different B0s and B1s. And then what you do is when you actually try a specific line, when you try a specific line, what you do is you figure out all of the residuals that go with that line, which is these vertical distances here. Like this. How far up and down from the line we are. It's not sideways, it's up and down. And you square all of them and add them up. And you try and choose the B0 and B1 that make that total the smallest it can possibly be, which is the reference to the least squares. So you find the residuals and then square them and add them up. So that's the procedure. And then what you do is you choose B0 and B1 so that this is as small as you can make it. Yeah. Because the closer to 0, the closer all these dots are to the line, and therefore it's the best line. There are other ways to make this choice, but this is a good one, and it has some good maths properties that make it easier to figure out the answer. And so that's why it's called least squares. I don't know why the ordinary. There must be an extraordinary one. It's called ordinary least squares. But the least is referring to making this total the smallest, and the squares is referring to the squaring these things. And one of the reasons we square them is so that the negative ones count the same as the positive ones. Because if you add them all up, including the minuses, it'll all come out to 0 anyway. And so, well, it won't. Like if you come down here, that won't. But you just make the squares the smallest. And there's a good reason for that, and because then you can use Pythagoras's theorem to help you solve the problem. So there's some decent multi-dimensional geometry going on, which is why Fisher was so clever. Like this was all obvious to him. And he refused to explain it to anything he thought was obvious. So tradition in statistics teaching has continued to this day. So that's what it's called. And you could imagine trying lots of different ones, and trying them all. And theoretically, a computer could do that. It could just try lots of different ones and see what happens. But it doesn't do that because you can use some calculus. Because finding the smallest answer for something, you can do derivatives and set them equal to 0, and it's blah, 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 blah. And there's actually a formula for what the correct one is, rather than having to actually try them all. So it's like, don't have to try different B0 and B1s. And use a formula, which is really convenient and nice. And so when Excel is calculating them, it's just doing that formula. And the formula is this. The correct choice for a beta 1 hat. So it became tradition after they invented mu for mean and x bar for mean to just stick a hat on the thing for the estimated version of the thing. Because beta 1, you'll never know. It's the one that is really true when the universe does this thing. Beta 1 hat is the one you're calculating. And there's a formula for it. And did I write it down? Because that would be bad if I didn't. I did, I'm sure I did. Curse me. I think it's SXY on...
SXY on S squared X.
Yeah, little SXY on SX squared, like that. Yeah. And what these are, this is the standard deviation of X, the little SX. So that's the sample standard deviation of X. And this is called the sample covariance. So this is a measure of how much y varies when x changes. That's what the SXY is. And this is a measure of how much x varies. And so you go, well, this is how much y varies overall. And you got to divide out how much x varies to get the total amount of variation in y. That's the idea. And there's a formula for this. You got to add up for all of the, so we do the sum across all the rows in the data. That's what this is saying. And we do xi minus x bar, yi minus y bar. So this is how far x is from its mean. This is how far y is from its mean. And for every row in the data, we multiply those two things together and then we add them up. You have to have at least some information. There is a shortcut version of SXY. And it will just take me a moment to remember what it, oh no, just wait. We've got to divide it by n minus 1, sorry. But don't forget that bit. Yes, cool, thank you. I'm glad I noticed that. It's because you've got to average it out. And the reason the n minus 1 is, there's some good reasons why, because it all comes out to be slightly off the correct answer if you don't do that, if you just divide by n. So there is a way to do it. And you bear with me. I may have to look that up. So there's a way to do it based on the sum of x times y and the mean of x and the mean of y. So you have to be told at least one thing. Give me a second. It'll just take me a moment to do the maths. So there's a very slightly shortcut version, because this one requires you to do a multiplication in every row of the table. So this is like, I'm just going to put a little note here. So you do multiply for every row and do the total, right? So we do the multiplication first and then we do the total. Whereas you can do this. That's an alternative thing that will produce the same answer. So there's still a multiplication for every row of the table. It's just you don't have to calculate the mean subtracted for every one of them. You can just do that after. So this is saying that you can do xy times yi, and then add it up, and then find out the mean separately and just take off n times that product, and it should come out to the same answer. This should be somewhere in the notes. But so theoretically, they could tell you what this is and what x bar and y bar was, and that would be enough to figure out SXY. Or if you don't have that, then you'd have to have the whole, it's just as quick to do either one, right? If you're using Excel and you're doing products and stuff, it's just as quick to do this. But this is ever so slightly quicker because Excel already has a function for multiplying the matching bits and adding them up. It's got a sum product function that does that automatically. So that's kind of cool. But this is philosophically what we're trying to do. We're going to say, well, how far is x from its mean and how far is y from its mean? And then we're going to multiply them together so that if they're both far away from their mean, you get a big number. But if one of them's close, but the other one's not, then you'll still get a small number. And so it'll all work out. And if they are perfectly aligned on a straight line, this answer will be 0. Not 0. Well, this answer will be 1 when you figure it out. Yeah, not 1. Not 1. just as big as it can be. The correlation's 1 if they're on a straight line. Got that wrong. So that's beta 1. And so beta 1 involves both the x and the y because that's what it's about. And you really can't get it unless you have a few bits of information about the data. But it's theoretically possible if you tell them, if they tell you this sum and the two means, you should be able to do it. Okay. And then beta naught, you calculate from beta 1. So I can never remember how to do it, but I do remember this. You sub x bar and y bar and beta 1 into the formula. Like, you know how it's like y equals beta naught plus beta 1x plus an error. That's how it normally goes. What you do is you stick all of them in, and that's correct. This is truth. And so therefore beta naught hat is y bar minus beta 1 hat x bar. So if you already know what beta 1 is, you can use it to figure out what beta 0 is. Yeah. And that's the quickest way. Like, there probably is a direct formula for beta naught hat, but it's just easier to do this. Is that okay? But I can never remember this formula, but I can remember that because it looks the same as the other formula.
Variables they give you from the regression line.
Yeah.
Or like any values they give you and then substitute in B1.
Yeah. And just remember what you use is x bar and y bar, like the mean of x and the mean of y. So even if they're not actually an existing point in the data, you just sort of go, oh, I'm going to average the x's and average the y's, and it's guaranteed to be on the line of best fit. It's y bar, yeah, the mean of y. So, yeah. Not yi and x, but y are the mean of y's. And this is not xi, but thank you for putting that in. That's going to be really useful for people who watch this. Yeah. Yeah, and so that works. It gives you the closest line in the sense of, oh, this sum of squares being as the smallest it can possibly be. And that will work whether your things are normally distributed or not. It is definitely the best line, no matter what. But if you want to do regression, if you want to do a hypothesis test, you have to make assumptions about normal distributions. So this will always be the best line of best fit. And so then what you'll say, then once you've got your beta naught and your beta 1, then you're going to say that the predicted y, just trying to make sure I don't lose my pages. The predicted, so now you've got it and you know where the line is now. So now know the line, the regression line they call it, or the regression equation, or the line of best fit. They're all the same thing. The correct regression line. And that's saying that essentially that y is going to be beta naught hat, whatever that number is, beta 1 hat times x. That's what you're saying. That's what the equation of that line is on the graph. But the thing is, you know for sure that's not going to come out to the right answer for y every time because it's all like wiggly, right? That's just going to tell you the answer for y that's on the line of best fit. And so what you're going to say is that the predicted y is that. You say that the best, you've given a specific x, the best prediction I have for what y should be is the one that's on the line of best fit. And you call it y hat. Yeah. So this is the line of best fit / regression line / regression equation. Yeah. And so you need to have the hat on the y. And so technically it's this with little eyes there. You need to have the hat on the y because you're not predicting the actual value of y. You're only predicting where the line of best fit is. Yeah. Okay. So we're getting there. We're nearly there. And now that we know what the predicted value of y is, we can figure out what our estimate for the error is, which is the residual. Am I able to have a look at that, my uni again? Not the electron, but the other one. For reasons that don't make sense, and well, it's not epsilon I hat, because that would make sense. The residual. And just remember what the residuals were. The residuals were how far away from the line we were. That's what ui hat is there. So that residual is what the actual value of y is minus the predicted value of y. Because the predicted value of y is the one that's on the line, and the actual value of y is, this is what yi is here, and this is yi hat there. So I'm just going to zoom in on that with my little magnifying glass. So there's yi hat, which is on the line, and there's the real value of y, and this distance here is the ui hat. That's what your lecturer has called it. Other courses just call it r for residual, and that would make sense. But anyway, here we are. So officially ui is a random variable. Yeah, they use r as well. Of course they do. That would be.
That one, if it equals, the closer it is to 1, the more.
Oh, that's a different r. They use small r for this in some courses and capital R for something else. Yeah. Okay. And the thing is that if it's below the line, then this will be a negative number. So it's positive if the point is above the line, and negative if the point is below the line. Yeah. ui hat. Yeah. And that's how I know why the subtraction is this way around. So that if this is higher than this, it comes out to a positive number. Because it could be the other way, but it's this way. Yeah, because positive is above and negative is below, and that makes sense. So cool. All right, so they are the residuals, and there's one for every row of the data. Cool, cool, cool. And yi hat, we know what that is. That's based on this formula here, right? All right, right. And then
But yi is any value of y there.
yeah, yi is the value from the data, and this is the predicted value from the formula. So this one's from the data, and this is from the regression equation. Yeah. All right. And then we're really good. We're so close. Right. We're nearly there. So now we know how these are our estimates for what the errors are. And now we know that we can start to make a good guess at how variable those are. So how variable is it to be, how the distance from the line, how variable is that? So we need a standard deviation for that, and that is SE. So the measure of how variable this error residual is SE. It's a standard deviation, sort of, and it will be the standard deviation of, oh crap, wait. First, find what they call SSE, which is the sum of the squared errors. And that is literally the sum of the UI hats squared. So we know that this has been chosen specially, like our line of best fit has been chosen specially so that this answer is the smallest it can possibly be. That's how the whole thing was designed. But it's not zero unless your things actually lie on a straight line. And this is the same as this. In your notes, it's yi minus yi hat squared. That's the same thing, right? Because that's what ui hat is. Ui hat is yi minus yi hat. So, but in the notes, they say this. But it's the same thing. Because that's ui hat is this. Okay. And there's a shortcut formula for this in the notes, and it is this. So there's a shortcut. Shortcut is n minus 1 times the standard deviation, the variance of y minus sxy squared on sx squared. So officially, you can figure out this thing from the standard deviation of x and y and from the covariance. I've never seen this formula in my life, but I'm not surprised that it exists. So, so that's a shortcut. That means that you don't have to actually figure out. Officially, you can figure out this SSE without even knowing what beta naught and beta 1 are, which is kind of cool, actually. It's pretty cool. But this, to calculate this, we'd have to figure out what beta naught and beta 1 were and calculate what y hat is using beta naught and beta 1 for every I, and then subtract them and then square them, and that's a lot of work. Whereas this directly gives you the correct answer. And this bit here is almost the same as beta 1 hat, except beta 1 hat doesn't have the squared there. I just want to be sure that I've got that right. Beta 1 hat. Yeah, look, beta 1 hat doesn't have the squared on the top there. So you could theoretically times beta 1 hat by sxy and it would do the trick. But anyway, wow, that is a surprise. Okay. So there's a shortcut for it, but this is the one that most people think of. It's the square of the distance between the real value and the predicted value on the line of best fit. And we know that that is going to be the smallest that SSE could possibly have been, because if we'd chosen a different beta naught and beta 1, then it would have come out to a different answer. But the theory tells us this is the smallest it could possibly be. Okay, that SSE, first we calculate that. Cool. And I'm really getting, yep. And then I divide it by n minus 2. So the SE is the square root of the SSE divided by n minus 2. For reasons that I'm sure Fisher and Pearson would have refused to explain to us. We were getting really close to making a variance. Like when you add up a whole lot of squared things with a subtraction, that's what a variance is. But we're having to divide by n minus 2 instead of n minus 1 because we had to calculate two things. When you do a variance, you calculate the mean first and then you do all the subtractions and the squaring. And so you divide by n minus 1 because we had to calculate one thing first. But we have to calculate the beta naught and the beta 1 first. So we had to subtract 2 because we had to calculate two things before we could figure out this variance. That's the basic reason why. So if you had a more complicated formula with two different flavors of x, you would have to do n minus 3, which comes, if you do econometrics, that would be next time, but maybe you won't, because it's not in that degree. But just warning you that that's where we're going in the second year courses. So that's that. And this is a measure of how variable all of these distances from the line are.
How variable.
Yeah. Yeah. And that is called there's a word for it. It's called the residual standard error. I think it's called the residual standard error. So, and this SE is like standard error, but it's also the standard deviation of the error. Cool. And now we have that. That's great. That's an estimate of how variable our data is. And then we can calculate this thing, the standard error of beta 1 hat. That's the standard error of the slope. And what this is saying if we imagine all of the data that we could have collected. So we're imagining we collected like 100 bits of data. What if we collected 100 other bits of data? Every time we collect 100 bits of data, the beta 1 would have worked out to be a slightly different number. And this is trying to be an estimate for how variable those possible beta 1s we could have had are. So yeah, it's an estimate of how variable the beta 1 could have been. Beta 1s could be. That's what it is. So this is where we're getting into real hypothesis testing scenario. All of our other standard deviations are just literal standard deviations of how variable the data we've actually got is. But this is the point in hypothesis testing. When you switch to hypothesis testing, you're imagining all of the data you could have collected. That's what hypothesis testing is about. You go, oh, okay, cool. I've got my data and I imagine all the data that could have been and compare mine to all the things that could have happened and go, well, mine's not that unusual compared to things that could have happened. And so I don't think there's a relationship. Or mine's really unusual compared to the ones that could have happened. And so I think this is unusual. And so really there isn't a relationship. And so this is an estimate of how variable the possible beta 1 hats could have been based on collecting all the possible other data, which you never know for sure, right? This is an extremely varied probability thing. And this is an estimate of how variable the possible beta 1 hats could have been. So we're nearly there. We can now ask a hypothesis testing question now that we have this thing. And this thing is calculated this way. It is SE on the square root of n minus 1 times the variance of x's. I don't know why they went to all the effort of putting something squared under a square root. That seems like a waste of everyone's time, but whatever. That is an SX squared, and that is SE not squared. So this is the same as this, like SX root n minus 1, like that. Whatever. I suppose officially you calculate the variance before you get the standard deviation because you have to do all the squaring and then you square root. So maybe this makes more sense, but whatever it is. So this is the standard error of beta hat 1. And if you've got Excel, it'll calculate this for you, right? You don't have to worry about any of that. Okay, so we're now up to hypothesis testing, right? This is part of the hypothesis test. Okay, So here's the question. A hypothesis test is an answer to a yes or no question. So even though regression does not ask a yes or no question, it asks, what is the formula that best predicts y from x? That is what regression is asking. The goal of regression is the formula itself, that regression equation. And we got that pages ago, right? We got that back here. We were at that, 2 pages ago. But there is a good yes or no question that goes with how can I predict y from x? And the question is, can I predict y from x at all? That's a good yes or no question. And so that's the question. Is there a relationship like this between y and x at all? So to answer this question, is there a linear, it has to be a linear relationship, between y and x? Is there one? That's a good yes or no question. And hypothesis tests can answer yes or no questions. They give you a p-value and you go, aha, or a test statistic. You get a p-value and your p-value comes under 0.05 and you go, yes, there is a relationship. And if it comes up above 0.05, you say, no, there is not a relationship. And you don't say it so hard and fast. You say, there is strong evidence of a relationship, or there is no evidence to suggest whatever. You never say it. It's never there is or there isn't. It's always there is evidence. Because we never know for sure. That's the problem with statistics. Statistics is trying to honor the fact that we never know for sure, but still get something. So that's what the hypothesis test answers. And so you have to turn, this is a very reasonable question that makes sense in context. But in order to make your statistical calculations work, you have to turn it into a statistics question. And so the best way to turn a research question into a hypothesis test question is to reference one of the parameters. Did I use that word in your course, parameter? Yeah, but it's to reference one of these numbers that we will never know. So when you're doing things with means, you're referencing a true mean that you will never know. You only ever know the sample mean. So you have to reference one of those numbers you never know. And the number that you'll never know that tells you whether there's a relationship is this one. Because if that number was 0, then that's saying that the best way to predict y is just random. It's saying that there will be some number and then plus or minus random stuff that isn't related to x at all. If that beta 1 is the number 0, then it's 0 times x, and x isn't actually in the formula at all. So my null hypothesis, which goes with there's no relationship, is that beta 1 is 0. The real beta 1, not the one with the hat, the real one that we're trying to figure out what it is. So this says that xi is not in the formula, right? That's what I'm thinking. That's what beta 1 being 0 would mean, that xi isn't in the formula because it's times by 0. All right. So that's my null hypothesis. So your null hypothesis always goes with, it doesn't always go with the answer no. It does go with the answer that has only one way to be. There is only one way to not have a relationship, and that's to be random. But there are many ways to have a relationship. And so there's only one way for this to be 0. There are many ways for it not to be 0. And so that's a good way of choosing null hypotheses. It goes with the one way to be. So back in when you're doing t-tests and you're saying, the null hypothesis does, damn it, just a second. Does the nationality of your person make a difference to how much they spend? And you go, okay, so my Australian people and my everywhere else people, do they have the same mean spending? There's only one way to be the same. There's lots of ways to be different. And so the null hypothesis is that they are the same. So that's the idea here. There's only one way for this to not have a relationship, and that's for this to be 0. And then your alternative hypothesis is almost always with regression that it's not zero. It is theoretically possible to have a one-sided one where it's greater than zero or less than zero. Hate one-sided tests. Yeah, well, your lecturer in my uni was extremely explicit, and they put it in bold and said, with regression, it's almost always a two-sided test. So it was in bold in my uni. They still did an example with it being one-sided. Yeah, so there's one-sided ones for other things, but in the regression section, your lecturer had in bold, regression is almost always two-sided, which is the not equal. The not equal, because there's two ways to not be equal. There's the positive side and the negative side. So yeah. So now it's a hypothesis test, and it's about the number beta 1, which we don't know. And that means we have to compare, based on beta 1 being 0, we have to compare all the beta 1 hats that we could have gotten to the one that we did get, which is why we need to know this. And so what we do is we do a t calculation. This is my test statistic. Yep, and it's always this. It's nice. And then you got your test statistic, and your test statistic is the thing that you calculated compared to what we imagine it is in my null hypothesis, divided by its standard error. So we're saying the beta. So if this wasn't 0 in this spot, you put another number here. Like if you wanted to know whether the slope was 10, you put 10 here. But we're putting 0 here because we're interested in whether it's 0.
Yeah.
Yeah. And so that's why, I mean, you're going, why have you put -0? It doesn't do anything, David. It's because this is the shape of a null hypothesis, even if that wasn't a 0 in that spot.
B1 is 10.
Yeah. You could put a 10 in that spot there. It's nice to know the what ifs. And so your Excel will calculate the t-statistic for you, but this is how to calculate it. So I have seen exams, not for this course, but for other courses, where they've given you the Excel output and then they've rubbed out one bit of it, and you've had to calculate that bit yourself. So in the table, it will tell you what beta 1 hat is, and it will tell you what the standard error of beta 1 hat is. And then, yeah, 0 is what you're trying to test. And so they'll say, what is the t-statistic? And normally you just read it off the table in Excel, but you could theoretically calculate it from the other bits. So it's classic. So this thing is a test statistic, and it will come out to some number. And what you have to do is compare that test statistic to all of the other test statistics that could have happened. And what those test statistics that could have happened is the t-distribution, which you look up in the t-table. And so the distribution of t, if the null hypothesis is true, is a t-distribution, which is why it's called t. Or it's the other way around, like they called it t and then they went, we need a name for this distribution, let's call it t, because they only use it for t-statistics. So the distribution is a t-distribution with n-2 degrees of freedom. So degrees of freedom is a very puzzling word. It's almost got something to do with you could change that many y values and still be able to figure out what the last two are to still get the same slope, basically. Yeah, but ultimately it's just the distribution finder. You go and look up the correct row. It just tells you which row it is. Because there's a different t-distribution for every sample size, right? And so just go and look up the right one, and that's the right one. And I mean, once you get past 30 for the degrees of freedom, it's very close to the Z distribution. So yeah, anyway, like it's really, really different down at the bottom, but it's really quite close at the top. So just bear with me, and I'm just going to see if I can go to my email, which is not going to appear on the video because that's great. Fingers crossed it comes up. Ah, crap. I don't have the same SharePoint as you, so I can't see it. But that's okay. It was just on, you just Googled it anyway, didn't you? That blue one, right? Oh, come on, you stupid machine. Just want you to show it to me. Now it's trying to advertise things. Some days I hate Google, but then it still gets me stuff, so it's fine. That's the one. Yeah? All right. For those watching, I've been just trying to make Google get stuff for me. So I'm just going to come back to Zoom and share this, which is, there's a copy of this like week 6, I think you said, or 7 maybe. So what this table tells me is if I pick a particular degrees of freedom, so if I had 20 pieces of data, I'd go to n-2, which is 18. And I'd follow that row along until I got to where my t statistic was. So if my t statistic came out to like 1.8, I'd go oh, it's between here and here. And that means my p-value is between 0.10 and 0.05. So this table's backwards from how the Z table works. So with the Z table, you look up your number and the probability is on the inside part of the table. But in the T table, the numbers for T are on the inside and the probabilities are at the top. Whereas the Z's the other way around. The numbers are on the row and column of the table and the probabilities are on the inside, but the T table's backwards. Alternatively, you can go and say, well, if I was looking for a 0.05, that'd be here. And you could go and find the matching T that goes with that, which is 2.101. That's right. So if your significance level was 0.05, which is tradition, if your level was 0.05, you'd go find the matching T statistic for your degrees of freedom, and that's here. And then you'd look at your T and see whether it was further out or further in than where you were. And further in is retain, and further out is reject. Do they use the word retain in this course, or do they just say don't reject? Yeah. Further out is reject, and further in is do not reject. As I said, every course does statistics with slightly different words, so that's why I have to check. That's how it would do, and you would have to compare your T statistic to that. With the Z table, you can look up your exact Z statistic and figure out the probability that goes with it. But T, there's just, because there's one for every degrees of freedom, they just don't have enough room to do all of that stuff. Which is why most modern statisticians just have a formula in the computer that does it for you. Like you go, oh, this is my T statistic, and it just gives you the p-value, which is what Excel does. So I'm just going to make an Excel sheet. Theoretically. I have to share it so that it comes on the video. So this was my X. Really? I just have some nice, why? They've just upgraded my computer and now everything sucks. Anyway. And I'll do it again. I'm going to have 20 data points. This is probably going to come out to no relationship because I'm just making up random stuff. But I'm just picking some random numbers, okay? This is not real data. So that's my original data. It's random. I'm just making up crap. And if I want to do a regression, I mean, the first thing I should do is probably draw a scatter plot. Ta-da! So you can see there is no particular relationship between X and Y there. And there shouldn't have been because I just made it up. If I'd been concentrating, I probably could have set it up better than that. Actually, if I make these 3s and 2s and 3s. Oh, not that one. That looks a bit more like a line coming downwards. Maybe I'll move one of these ones as well. Let's move X is 1 and Y is 5. There we go. Just to make me feel better. So you can see actually only moving a few points can actually make it look more like a straight line. It'll probably still won't come out as significant. And then did they get you to do it in the data analysis thingamajig? Like, yeah, they. Oh, damn it, I have to turn it back on again. They got you to do like the analysis toolpack thing, didn't they? Yeah, there it is. Well, now you know how to get it in a Windows computer, how to turn it on. I'm going to go to regression. This is how they got you to do it. And there's my Y's. And there's my X's. And it does have labels. And I'm just going to stick it over here so that I don't have to look at a new page. Ta-da, there it is. Yep. So see this T statistic here? That would be this number divided by this number. So if I go like whatever's there divided by whatever's there, 10.87031. And that's because this is the beta 1 hat, and this is the standard error of the beta 1 hat. Correct, that's the one. And this T statistic is testing is beta 1 0, that question. And then the p-value is 2.4 E0 minus 9. So that means that it's actually there's 9 zeros, like 0.00000000244. So that is deeply significant. As it is, like T statistics 10, when you looked at that T table, most of the critical ones were like 1 point something, and this is huge. So that's really big. A really big T statistic goes with a highly significant result. Yeah, and so there it is. That's what it is. And this is the equation here. It's saying the equation will be, oh no, that's the intercept. Damn it, David. This is the beta 1. See, it says intercept. Intercept is beta 0. So it says intercept, and it will have the label that goes with your X thing here.
Like that, it said, is there a relationship?
You'd look at this one.
That.
Yeah.
And what would you say?
That is still under 0.05. It's under 0.01 even. And so I would say it is significant at the 1% level. And I would reject. Yep. Sorry. It is a low p-value. Yep. Yep. Rejection region usually refers to the T's, but it's also the p-value rejection region. So it's under 0.05, and so we reject. But that T statistic is So I would look at this. So my degrees of freedom was 18, right? Because we had 20 observations there, 20. Degrees of freedom is n minus 2, so 18. So I would go and look at the t table. There's my t table. Here's row 18, and the 0.05 number is 2.101. So that's for the two-tailed 0.05. And my row 18 at that level is 2.101. And so I would look at my t statistic and go, my t statistic is 3.36, which is further out than 2.101, which is in the rejection region. So that is, yeah. So it doesn't matter that it's a minus 3.36, it just matters how big the number is for the purposes of a two-tailed test. So it doesn't.
Would be.
Yeah. So, yeah. And listen to the video. I'm just going to put it on the notes here. Interpretation things. So you can either do it directly from the t statistic and look up the correct t that goes with your p-value, your significance level, or you can look at the p-value and go, that's below. So just to absolutely be clear on that, you get to choose depending on the information you've been given. So yeah, so I'm just going to draw some of that stuff. So the idea is that you'll get a t statistic, your test statistic, which we just had, that was my t. And it'll come out to a number, right? And you'll know that it comes from a t distribution with n minus 2 degrees of freedom. So if you want to use the table, you can look up row n minus 2 in the t table and find, so there's two ways of doing it. You can look up row n minus 2 in the t table. You can find the column for 0.05, for example, two-tailed. That's what I did. And there'll be a number in that spot. So e.g., for 18 degrees of freedom and 0.05 two-tailed, you get 2.101 it was. Yep. From the tape. That's right. Some people call this the critical t-value. I don't know if your lecturer uses that word. Yeah, so this is a, so what we need to find the critical t, which is, this is how we do it. Yeah, the t critical is 2.101. And what you want to do is you want to compare this number you've got to that one. If this number is further out from 0 compared to that one, then it's in the rejection region and you reject. So if your t equals whatever is further out, then reject. If your t is whatever is, then the t critical. Further in, then retain. And the picture that goes with it is this. This is what a t distribution looks like. To the naked eye, it looks like a normal distribution, but the computer knows better. And you've got your t critical at some point. And the idea is that the minus version of the t critical is over here. And if your t actual one from your data is out here on the outside, then you reject. And if it's on the inside, then you retain. Then you do not reject, sorry. That's how. And this probability here, this area for the t critical is exactly 0.05 or whatever it is, like whatever your significance level is in the shaded region. So if your t star is in here, if your t from the data is here, then reject. So the thing is that this area here is 0.05. And this area here is like 95%. That's right. The confidence, like this T critical is also the number you use to figure out a confidence interval. So if you wanted a 95% confidence interval, you would use this number as well because it has exactly 95% in the middle.
It's like they gave you two times 0.5. It would be confidence level.
Yeah, exactly. Yeah, that is exactly true. So if your significance level is 5%, or 0.05, then the confidence level is 95%. And if the significance level was 1%, the confidence level would be 99%. That's how they go. And you use the same critical for both. Same critical T for both of them. Yeah. And that's because like confidence intervals and hypothesis tests like do the opposite thing to each other. Like they're designed to answer the opposite question. So the hypothesis test asks is beta 1 0? And the confidence interval says, what is beta 1? And so they're trying to do the opposite question to each other. One of them saying, is it this specific number? Whereas the confidence interval says, all of these numbers I'm happy to believe. So they do the opposite job. And that's why if you have a confidence interval, if 0 is not in it, then you reject. Because the confidence interval is all of the numbers you are okay with. Like they're all the ones you wouldn't reject.
Oh.
Yeah. So they're the 95% that you wouldn't reject. And so if 0 is in there, then you won't reject it. But if it's not, then you will. Like they're the exact opposite things, confidence intervals and hypothesis tests. They use the same data. They use the same critical T. They're answering the same question, but in the opposite direction. Like one says, what is it this number? And the other one says, what are the numbers that it is? And so theoretically, it would make more sense to just give confidence intervals because then people could answer the hypothesis test for all the numbers. But that's just not how it's done. We're stuck with it now, unfortunately. It's about 100 years ago that this was all invented. It was 1925 when the book was published on p-values. We're stuck with it now. So, yeah. So, yeah. But the other thing you can do is look at the p-value directly. Because the p-value, the critical T is the one that would give you a p-value of exactly 0.05. So if your actual T is here, right? This is the T from the data, not the one from the table. And you color in this area, that area together is the p-value. And the critical T is the one where the p-value would be exactly 0.05. And the numbers that are further out, that area has got to be smaller. So further out, that means the area is smaller. And so that's why T gets bigger when you reject, but the p-value gets smaller when you reject because the further the T is, the smaller this area is. Yeah. So they go in the opposite directions to each other. The reason we have p-values is because it's like this standardized thing that no matter whether you're doing a t-test or a z-test or a chi-squared test or an f-test or all the different kinds of tests that there are, you haven't seen f-tests, but no matter which one you're doing, you can convert them all to p-values. And then it's a standardized thing. You can just look at the p-value. Whereas if you only ever do t-tests, then you can use t. But if you have to use different letters for different things, then the p-value is a standardized thing that always works. So yeah, but the reason why it's interesting to know p-values is if you ask a computer, you don't need to look up the critical T, you just look at the p-value. So if your computer says the p-value is 0.003, then you'll say that's below 0.05, and so you reject. Or whatever the level is they want it to be below. So the point of a p-value is that you don't have to look up the critical value. You just know that the critical value for a p-value is 0.05. Yeah. So the problem is that one of the reasons this course is taught this way is because different people, even in economics, have different preferences for which one they use. And so you have to be prepared when you read something written by an economist to cope with any of them. So that's why you get taught them all. Because ultimately, any course, whether it's a maths course or not, is partly about communication and about knowing how people talk about things in the discipline. Well, now you know, sometimes people do p-values, sometimes they do t-values, and you have to cope with both. So the best way to tell if you can cope with both is to know that you can produce them both. Correct. And vice versa. They match up. And so the critical t is the one that would give exactly 0.05 for the p-value. And so that's why you know that, well, I just have to compare it to that, and then it'll be okay. T, yep. Two, yeah.
Find the
Critical one. Correct. Yeah. So that is, I hope that was helpful. I'm going to stop the recording there.